Thanks for tuning in my work on VarVE, where we try to bring SIMD performance to the variable with values. I want to apologize for my visa issue and for not being able to present this work physically. This work was done while I was a PhD student at the University of Chicago, advised by Professor Andrew Chen. Almost every architecture presentation has a slide on technology scaling. Here it comes mine. Technology scaling has been enabling processor datapaths to grow wider. We have seen scalar datapaths growing from 8 bits in Intel's 8008 to 64 bits in most recent mainstream processors. We have also seen the growth in vector length in SIMD, where same operations are applied to multiple data from 64 bits at its start in the multimedia extension to 512 bits recently with the AVX. Moreover, vector length agnostic SIMD, like ARM's scalable vector extension and RISC-V's vector extension, are proposed such that a single version of the program can work seamlessly on hardware with different vector lengths. Maybe the previous sessions on RISC-V already covered this, but the key for vector length agnostic SIMD is that the vector length is a runtime constant reported by the hardware. The program shown here is a simple A times X plus Y vectorized with ARM SVE. The two vector strips are loaded first, and the linear combination is performed before the results are written out. It is this SVCNTB special instruction that reports the vector length from the hardware, paces the strip mining process. The wider the vector length reported, the longer the vector strip, and the fewer number of iterations there are. However, real-world values are more diverse than just being power of 2 wide, as supported by the scalar or SIMD SS. Values are diverse in bit width mostly because the bias, precision, and range in the digitalization process. For example, the credit card transactions may be represented by 1 to 24 bits, depending on the transaction amount, with upper limit being the credit limit. There are other countless examples like this in the real world. With lack of ASA support on expressing values with diverse widths, zero padding are added to fit these values into 64-bit or 32-bit data paths. This leads to wastes inside the main memory, caches, and registers, as well as the ALU. Carrying and computing the padding values as drawn in red in the figure. The SIMD ALU faces the same issue. With the padding for element-wise alignment, many ALU positions are taken up by the padding zeros and thus wasted. All in all, the data path efficiency is low for lack of proper support for values with diverse bit width. Recent advances only address a portion of problem around data path efficiency. BSNE takes advantage of a delicate mathematical properties called binary segmentation to compute vector inner product or vector linear convolution on narrow values via multiplication of integers packed from those narrow values. There are also various floating point formats, including bfloat proposed, trying to make better use of data path bits in neural network workloads. However, this work cannot provide general compute support for values with diverse widths. Particularly, they cannot gracefully handle outliers, so programmers would continue padding values to a higher bit width, 32-bit or 64-bit, just to be safe for outliers, wasting on padding bits in all places of the data path and resulting in poor efficiency. To address this, we designed VarVE, a vector extension providing SR support for variable width values. It features mainly two parts, both built on and integrate gracefully with the vector length agnostic SIMDs. The first is the efficient packing, unpacking, we call it PUP, to load or store variable with values. The second feature is efficient direct computation on the variable with values. First, PUP. To provide support for efficient load and store variable with values, we design two kinds of instructions. One is to declare a stream via data pointer, stream description, and total number of bits. The exemplar intrinsics here showing FR stream is for bit packed streams specifying the width for each value. Another instruction, unpack, actually triggers the unpacking of the stream values into a vector register. More instructions describing different streams are also included, but they all share the same unpack instruction. The right example shows the expressiveness of VarVE's PUP. Vanilla SVE, without the support of bit-level manipulation, needs a complex sequence of overreading, truncating, and aligning to unpack a bit-packed stream into vector register to be further processed. But with direct unpacking support in VarVE's PUP, it is only two steps, as we just discussed. First, describe the stream, and then unpack from it. The second feature is to compute on variable with values directly. First, the vector register is designed to hold values with diverse widths by densely concatenating the values together. And one metadata register is added for each vector register to mark the bit width of each value stored in the vector register. This metadata register is invisible at SI level. It is only updated along with the updates to the corresponding vector register. Further, we include VarVE vector operations as listed in the table to provide general compute support. They are still element-wise operations between two native variable with value vectors, but with a special runtime semantics. The number of elements produced by each operation in the result vector is no longer statically defined. It is now a dynamic notion depending on the values and their widths the operation operates on. We will further explain on this on the next slide about dynamic strip mining. We have seen the strip mining process by ARM SVE. It is paced by the hardware reported vector length. VarVE's lockstep strip mining is somewhat similar, but dynamic, in the sense that the strip size, as in number of elements processed of an iteration, can change throughout the iteration. Here is an example where we add three streams of values together. An operation may produce less number of values than the operands if it faces back pressure, as the add operation producing V2 in the example. If result values become wider and the fixed width vector register cannot hold all the values from the operation, the last values are dropped. The last result values are dropped until fit. As the iteration proceeds, the strip size, as in the number of elements processed by one iteration, may gradually decrease as more operations face the back pressure. As a result, strip size in VarVE's strip mining is determined at the end of iteration. This is achieved by having each VarVE operation updating a shared special register with number of elements processed by that operation, and the special register only keeps the smallest update. At the end of iteration, the special register can be queried for the iteration's strip size, similar to SVE's SVCNTB. Putting it all together, we look into a filter example from a TPC-H query, where we get the customer key for all customers in the building market segment. First, the market segment column is loaded into the VarVE vector register with native support for densely holding variable with values. And then the predicate is produced by comparing the loaded vector with the building enum before using it to gate the packing of the customer keys. The dynamic strip mining process materializes as a special instruction RCNUME reading the strip size at the end of iteration, as well as the input stream pointer increments with the strip size. This program also showcases a special optimization we call masking optimization. If a predicate can be calculated on a fast progressing stream, in the example, the market segment column, it can be pushed down to other streams, for example, the customer key column, when unpacking values from the streams. This saves precious vector register bits towards the non-filtered values. Masking optimization is particularly useful for VarVE, as it avoids fast progressing stream being slowed down by slower progressing ones because of the dynamic lockstep strip mining. We also wanted to quickly note a few things about implementations being reasonable before evaluating the VarVE SM. Additional components are needed to implement VarVE compared to a conventional SIMD or vector length agnostic SIMD. First, as we already described, vector metadata registers are added to mark value width for each vector register. Then, an element alignment unit is added as an additional pipeline step to align the corresponding values before the VarVE ALU. Most importantly, the VarVE ALU unit is dynamically partitionable based on the element alignment to carry out the operation only using datapath bits as needed by the two aligned values. Please turn to the paper for more implementation details. In evaluation, we extended clan error VM with VarVE intrinsics and CodeGen to compare C++ code written with VarVE intrinsics. Gem5 is also extended with VarVE instruction encoding and performance modeling for the hardware we designed, including all adjustments and restrictions. Here comes the evaluation results. First, on kernels ranging from file system, scientific computing to neural network. On bitpacking workload, both PUP alone and the full VarVE with direct variable with value compute can largely outperform SVE by more than 20 times. This is not a huge surprise, as it is a workload directly targeted by the PUP feature. On pure compute workloads, PUP alone doesn't bring significant performance speedup over SVE, but with native support to compute variable with values, full VarVE wins 1.9 times speedup over SVE via improving datapath efficiency. We also observe similar speedups in vectorized filtering queries from TPC-H benchmark. Full VarVE is 2.1 times faster than SVE on average. Many of these speedups are contributed by the masking optimization. In conclusion, we find that native support on directly computing variable with values, as showcased by VarVE, is crucial to reduce data path weights and improve efficiency. Sophisticated stream packing unpacking alone is not sufficient to reap all benefits. As I am not physically presenting, I branch predicted a few questions that might be asked. Please take a look at the slides if you are interested. First one is on masking optimization. Why is it unique to VarVE and why it doesn't apply to conventional vector SIMD like ARM-SV? The second one confirms that all VarVE features can be built on top of RVV as well. And finally, on extensions to floating point support. It is somewhat a natural extension, but definitely a complex one in implementation. Thanks for coming to my presentation.